So another topic in differential equation is solving exact equations. So the first step in solving exact differential equations is to show proof that the differential equation is exact. So let's say we have a differential equation, mxy differential x plus nxy, n of xy differential y is equal to 0. We say that this is an exact differential equation if we get the partial derivative of m with respect to y, and it is equal to the partial derivative of n with respect to x. So therefore, if this is equal, if this is true, then this is an exact differential equation. Okay, so we conclude that this is exact. After that, after concluding that this is exact, we will use two statements to solve the exact differential equation. First of all, we say that the partial derivative of the solution, which is f, with respect to x is equal to m, or n, the partial derivative of the solution with respect to y is equal to n. So this is the next step that you will use. Then after that, you will come up with the solution f of xy is equal to c. So let's go ahead and have some example. So for example number 1, we have cosine 2y, quantity cosine 2y minus 3x squared y squared, differential x, plus closed quantity cosine 2y minus 2x sine y, sine 2y I mean, and then minus 2x cubed y differential y is equal to 0. So we have here our m, which is cosine 2y minus 3x squared y squared, and then our n, which is cosine 2y minus 2x sine 2y minus 2x cubed y. So for our m, we will get the partial derivative of m with respect to y. So the first step here is test for exactness. So if we get the partial derivative with respect to y, meaning to say our x is constant. So cosine 2y, the derivative of that would be negative 2 sine 2y. And then since x is constant, we have minus 3x squared, then derivative of y squared, so that would be 2y. So therefore, this is negative 2 sine 2y minus 6x squared y. Now let's go to our n. So we will now get the partial derivative of n with respect to x. Okay, so cosine 2y, this whole term is a constant. We will consider this constant because we are again getting the partial derivative with respect to x. And then here, 2 sine 2y, 2 sine 2y is constant. We just have to get the derivative of negative x, so that is 1, negative 1. So the negative would go here. And then last, we have minus 2y as our constant. And then derivative of x cubed, that is simply 3x squared. So therefore, this is negative 2 sine 2y minus 6x squared y. So we see that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And therefore, this is an exact differential equation. So after that, as I've said in the first slide, let's say we consider m, and m is equal to the partial derivative of the solution with respect to x. Okay, so let's go ahead here to our next slide, to our next sheet. M is equal to cosine squared 2y minus 3x squared y. So cosine 2y minus 3x squared y squared. Okay, let me just check. 3x squared y squared. So we start with that, and we say that m is equal to the partial derivative of f with respect to x. Okay, so partial derivative of f would now be, we will integrate cosine 2y minus 3x squared y squared, but with respect to x. Okay, we will integrate to solve for f. So this will become f, do integration, but our variable of integration is x. So we have f is equal to, so cosine 2y, differential x, let's just say differential x, cosine 2y is constant. Then integral of differential x, so that is x. Okay, and then minus, here we have 3y squared as our constant, and then derivative of x, integral of x squared dx, so that would be x cubed over 3. And then instead of adding c, instead of plus c, because we have held y as constant, then therefore this should be a function of y, t of y. So let's simplify. F is x cosine 2y, this one is cancelled, minus x cubed y squared plus t of y. What is t of y? So we will now use the second statement, that the derivative or the partial derivative of f with respect to y is equal to n. Okay, so from this is actually the solution, but it's incomplete because we still have to solve for t of y. So from this we will solve the partial derivative of f with respect to y and equate it with our n. So x is constant. X is constant, we will simply get the derivative of cosine 2y. So that would be negative 2 sine 2y. And then minus x cubed is constant, derivative of y squared, so that is 2y. And then plus t prime y. Okay, the derivative of t of y. So we now have the partial derivative of f with respect to y is equal to negative 2x sine 2y. Okay, negative 2x sine 2y minus x cubed 2y minus 2x cubed y, I should say, plus t prime y. And this is equal to n. What is our n? Our n is, let's just go back, our n is cosine, this one, cosine 2y minus 2x sine 2y minus 2x cubed y. So we have cosine 2y minus 2x sine 2y minus 2x cubed y. So that is our n. So if we equate the two, okay, so n is cosine 2y minus 2x sine 2y minus 2x cubed y. So is equal to this one, negative 2x sine 2y minus 2x cubed y plus t prime y. Okay, so what will be cancelled? This term will be cancelled because they are the same, and this term will be cancelled. So therefore, what is left is we have t prime y is equal to cosine 2y. And to solve for t of y, we simply have to integrate cosine 2y dy. Okay, so what is the integral of cosine 2y dy? So this will be integral of, our u is 2y, so 2 differential y. Okay, so the balancing factor is 1/2, and therefore t of y is simply equal to, so that is equal to 1/2 sine 2y. So we will now go to our final answer. And our final answer is, so it's derived from here. As I've said, this is the solution. We simply have to solve for t of y. And we have solved for t of y. So f is equal to the solution, x cosine 2y, x cosine 2y minus x cubed y squared plus t of y. T of y is 1/2 sine 2y. 1/2 sine 2y is equal to c. Okay, so to simplify this, we can remove the 1/2. Simply multiply it by 2. So 2x cosine 2y minus 2x cubed y squared plus sine 2y is equal to c. So that is the final answer. So let's go to our second example. So we have 2xy, quantity 2xy minus tangent y, close quantity, differential x, plus x squared minus x second squared y, close quantity, differential y is equal to 0. Okay. So our m here is 2xy. So remember, m is always with differential x. So just to standardize things, and n is always with differential y minus tangent y. So we will get the partial derivative of m with respect to y. So x is constant, so 2x is constant, derivative of y is 1, then minus derivative of tangent squared y is second squared y. And then n is equal to x squared minus x second squared y. So we will get the partial derivative of n with respect to x, and this one will be 2x. Since negative second squared y is constant, so we simply get the derivative of x, so that is 1. So we see that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So therefore, this is exact. Okay, so we will now proceed with let's choose. Let's say I chose n, because in the previous example I chose m. So let's say I chose n, and n is equal to the partial derivative of f. The solution is equal to partial derivative of f with respect to y. So that is equal to n, and n is equal to negative x squared minus x second squared y. So let's proceed. So we know that we will integrate. So f is equal to x squared, partial derivative of f, partial differential of x squared minus x second squared y. Then we will integrate with respect to y. Okay, so f, integrate both sides, is equal to x squared y minus x integral of second squared y dy is tangent. And then instead of adding c, we will add t of x, because we have held x as constant. So we will now proceed to the second part of the solution, wherein we will consider the partial derivative of f. Partial derivative of f with respect to x is equal to Rm. So from here, from this equation, we will get the partial derivative with respect to x. Okay, so the partial derivative with respect to x is, so y is constant, derivative of x squared is 2x, minus tangent y, that is constant, derivative of x, that is 1. So plus t prime x. And then we will equate this with our m, and m is equal to 2xy minus tangent y. So m is equal to 2xy minus tangent y. Okay, so 2xy minus tangent y plus t prime x is equal to 2xy minus tangent y. So we see that all terms are cancelled. Okay, t prime x is equal to 0. So therefore, t of x is 0. Okay, so the solution is simply x squared y minus x tangent y is equal to c. Okay, because t of x is 0. Okay, final answer. So last example. We will get the particular solution of this differential equation when x is 0, y is equal to 1. Okay, so we have 3y times the quantity x squared minus 1 differential x plus x cubed plus 8y minus 3x close quantity differential y. So what is our m? So for our m, we need to distribute 3y. So that would be 3x squared y minus 3y. And n is simply x cubed plus 8y minus 3x. Okay, so let's get the partial derivative of m with respect to y. So 3x squared is constant. So derivative of y is 1 minus 3. Partial derivative of n with respect to x is 3x squared. 8y is constant, so minus 3. So again, the partial derivative of m with respect to y is equal to partial derivative of n with respect to x, so it is exact. So let's say we proceed with m, and m is the partial derivative of f with respect to x. So 3x squared y minus 3y. So a tip here is you select what you think is more simpler between m and n. So I selected m because it only has 2 terms, while n has 3 terms. But it's up to you. It's up to the solver what to select. And you still arrive at the same answer. So we know that f is equal to the integral of these 2 terms with respect to, with x as our variable of integration. So we have 3y as constant. Integrate x squared differential x, so that would be x cubed over 3 minus 3y is constant, integral of differential x, so that is equal to x. So we simply have to add t of y. Okay, so 3 cancels out here, and this is equal to x cubed y minus 3xy plus t of y. Okay, so f is equal to x cubed y minus 3xy plus t of y. Okay, you just check. X cubed y minus 3xy plus t of y. Okay, next we will integrate with respect to y, because the next step that we will take is the partial differential of our solution with respect to y is equal to n. So let's get that. X cubed is constant. Differential of y is 1 minus 3x, and then differential of y again is 1, so plus t prime y. Okay, then we will equate this with our n. N is equal to x cubed, just get it, x cubed plus 8y minus 3x plus 8y minus 3x. So x cubed minus 3x plus t prime y is equal to x cubed plus 8y minus 3x. So x cubed cancels out, 3x also cancels out, and we're left with t prime y is equal to 8y. So t of y is the integral of 8 integral of y differential y, and that is simply, so this is y squared over 2, so 4y squared. So our solution will now be x cubed y minus 3xy plus 4y squared is equal to c. So this is the general solution. Okay, so what is our particular solution? The particular solution is defined by when x is equal to 0, y is equal to 1. So let's go ahead and substitute that so we can solve for c. Okay, so x is 0, 0 cubed times 1 minus 3 times 0 times 1 plus 4 times 1 squared is equal to c. So first 2 terms cancels out, and c is simply equal to 4. Okay, so substitute. We have x cubed y minus 3xy plus 4y squared is equal to 4. Okay, so I always prefer that my answer is equated to 0. So x cubed y minus 3xy plus 4y squared minus 4 is equal to 0. Now, that could be the final answer, or here we have y as our common term, x cubed minus 3x, or we simply just will factor out x as well. So xy, so this will be x squared minus 3y, and then here we factor out 4, y squared minus 1 is equal to 0. Okay, so we factored out y here, so let me just correct that. So y here should be erased. Yeah, x cubed minus 3 only. So it's up to you, no? But I will accept if the final answer is the first one. Okay, so those are our two final answers. So that's it for the video. Answer the discussion question that I will post. Thank you.